Everything looks fine in development. The API responses are coming back in milliseconds. The logic is solid, and honestly, you are feeling pretty good about the architecture.
Yeah, boy.
But there is a difference between a system that works and a system that survives. The moment you go live, the clock starts ticking. 10 users become 100, 100 become 1,000. Suddenly, those quick database queries starts taking longer. The CPU starts hitting 90%. This is the exact moment where coding ends and system design begins. In this video, we will not just look at individual tools, we will look at how a backend evolves as user traffic grows. Step by step, we will walk through load balancing for traffic distribution and handling concurrent users, caching to protect our database from exhaustion, CDNs for global speed, message queues, and database scaling. By the end, you will see how a small project scales into a production-grade system. Most application begins with all-in-one setup, one server, one application instance, and one database, commonly known as a monolith. Everything lives together, it's clean, cheap, and easy to debug, but it has a single point of failure. As traffic increases, CPU, memory, and database connections all compete for the same resources. To handle more users, we need to distribute the load. When one server hits its limit, the solution is simple: add more servers. But we cannot give our users 5 different URLs to try. Users shouldn't know or care which server they hit. That's where a load balancer comes in. Think of it as a smart traffic controller at a busy intersection. It sits in front of your servers, takes every incoming request, and directs it to the server with the most available capacity. It ensures no single machine is doing all the heavy lifting while others sit idle. If one server goes down, traffic is routed away automatically. Even with multiple servers, if every single request forces the database to scan millions of rows, things will still be slow. This is where caching comes in. Tools like Redis or Memcached. Instead of doing the hard work every time, the application stores the frequently used data in memory. It's like keeping our house keys on a hook by the door instead of searching the whole house every morning. This reduces the load on database and cuts down response times significantly. Now let's talk about static content. Our server might be in Mumbai, but our users are in New York. Physics doesn't care how perfect our code is. Distance will always add latency. A CDN or content delivery network handles our heavy assets like images, videos, and JavaScript files. It caches them on servers located physically closer to our users. If a file isn't available, the CDN checks nearby cache nodes. Only then it hits the origin server. Our main backend can focus on processing data while the CDN handles the heavy lifting of serving files. Eventually, the database becomes the final hurdle. We can scale vertically, buying a more expensive server with more RAM, but that also has limits. Then there is horizontal scaling or sharding. This is where we split our data across multiple database clusters, often by user ID, region, or tenant. It's complex, and it's usually where the most critical architectural decisions are made. If we get this right, we can scale almost infinitely. Not everything needs to happen now. For example, sending emails, notifications, analytics events. Instead of doing everything synchronously, we use message queues like Kafka or RabbitMQ to offload these tasks. The application pushes a task to the queue and responds immediately to the user. Background workers process these tasks at their own pace and scale independently. This keeps APIs responsive even under heavy load.